Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Kangaroo Point Green Bridge, a new iconic landmark for Brisbane. My name is Megan Purdy and I'm from Engineers Australia. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises a continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started today, I would like to acknowledge that today's webinar has been hosted with Engineers Australia's industry partner, Brisbane City Council. Brisbane City Council is the largest local government in Australia. Working with the community, they deliver essential services and programs that meet the needs of a growing city. They are building essential infrastructure, including new green bridges and Brisbane Metro, to support economic recovery and reduce congestion on roads. BCC are creating new leisure and lifestyle opportunities, including transforming Victoria Park into an iconic public parkland to make it easier to connect with the people and places that make the city great, and are protecting the heritage and green spaces and upgrading parks, playgrounds, libraries and pools in the suburbs. Now, today we will hear from two speakers, followed by our live audience Q&A, and I'd encourage you all to send your questions through to our speakers via the chat box. I would now like to welcome our moderator for today, Eliza Howe. Eliza is a group leader in Arup, Queensland, leading the disciplines of civil structures, building services, maritime and geotechnics. Eliza is also the project manager for Arup as the Kangaroo Point Green Bridge Technical Advisor and has more than 20 years of experience in the design of bridges and civil structures, with a particular area of expertise in the design and delivery of active transport bridges. Some of Eliza's other active transport bridge projects include the Gralpa Bridge, Indooroopilly Riverwalk, Botanic Gardens Riverwalk and the Cornwall Street Velo Bridge. Please join me in welcoming Eliza Howe.
Thank you, Megan, and welcome again to our viewers. I'd now like to welcome our first speaker, Jim Heffron. Jim Heffron has more than 33 years of experience working as an industry professional and has an extensive background in both design and construction infrastructure projects. Prior to joining Brisbane City Council's major project branch in 2006, Jim has experience across the private and public sectors, having worked as a consulting engineer with Arup, for Names, the contractor Nexo, and the Department of Main Roads Structures Division. Since joining Council, Jim has worked on both the Clem Jones and the Legacy Way tunnels, the ICB upgrade, and is most recently leading the Green Bridges program. Please welcome Jim Heffron.
Thank you for that introduction. We might now get underway with the presentation. First, I'd like to have an acknowledgement of country. Brisbane City Council acknowledges this country and its traditional custodians. We acknowledge and respect the spiritual relationship between traditional custodians in this country, which has inspired language, songs, dances, law and dreamtime stories over many thousands of years. We pay our respects to the elders, those who have passed into the dreaming, those here today and those of tomorrow. May we continue to peacefully walk together in gratitude, respect and kindness and caring for this country and one another. So, introducing myself, my name is Jim Heffron and I'm the Project Director for the Green Bridges program for Brisbane City Council. Iconic bridge projects do not present themselves too often, and it's an honour to present the Kangaroo Point Green Bridge on behalf of Brisbane City Council. Together with Bram Gruitz of Bessex Watpac, we'll take you through the development of the Kangaroo Point Bridge to date. Firstly, from a client's perspective, Council's planning of the project and procurement, before handing it over to Bram, our delivery partner, to focus on the engineering, design and construction aspects. Kangaroo Point Bridge is the first bridge to be delivered under the Green Bridges program, and the plan there, it's got it highlighted in red. Green Bridges is one of the key initiatives of the Transport Plan for Brisbane Implementation Plan 2018 and involves making it easier for residents and visitors to get around the city by foot, bike, scooter or connecting with general public transport. The concept of the Kangaroo Point Bridge crossing in this reach of the river has been around since the 1800s. Council's Phase 1 concept study was undertaken in 2014 that started to seriously look into the bridge crossing in this area. This initial study filtered through the range of possible crossings, alignments shown in the plan above. You can see that plan stretches from the areas from the Story Bridge through to Captain Cook Bridge. And this study was enabled to recommend 2 preferred alignments for future investigation. Then, as part of the detailed business case and reference design that was undertaken by Council, the Alice Edward Street to Scott Street alignment was selected. And that was mainly because it provided a gentler grade on the bridge and at landing points, providing greater accessibility for people with a disability that allows compliance with the Disability Discrimination Act 1992. And it reduced conflict points between pedestrians, cyclists and other vehicles due to less on-street parking around the Scott Street area and in simpler intersection layout at Main Street. And it also provided better opportunities for safer connectivity to the wider active transport network with more direct connections to Deakin Street. Now, this is the existing diagram of the existing network and also a view of the reach of the river that we're going to be placing the bridge. The problem is that there are currently limited and inconvenient sustainable transport options from and through Kangaroo Point. This is largely due to the existing network and natural topography, along with demand growth of where people intend to grow in the future. The distance between the Story Bridge and Goodwill is around 2.5 kilometres, and that results in a large gap in the walking, cycling network and access to the CBD for Kangaroo Point residents and ongoing riders. Daily traffic for the Story Bridge sees around 1,600 pedestrians and 1,300 cyclists every day. And for the Goodwill, it's up around the 10,000 pedestrians and 3,500 cyclists. So with population growth in Kangaroo Point rising, I think, from 10,000 to 14,000 in 2041, jobs in the Kangaroo Point area will increase, and Kangaroo Point's current isolation results in a much lower micro-mobility transport mode for Kangaroo Point compared to the Brisbane inner city area. So as part of the business case, demand modelling showed that the Kangaroo Point Bridge will reduce congestion on the existing pedestrian and rider transport crossings. It'll also provide for future capacity, with approximately 130,000 additional jobs are expected to be located within a 20-minute walk in 2031. So this is a perspective drawing of the successful Kangaroo Point Bridge design that largely follows Council's reference design that Bram will touch on later. It's an 8-span bridge which can be broken into 3 segments. Spans 1 to 3 being the city approach, and spans 4 to 6 being the asymmetrical cable stay structure located closer to the city and away from the Kangaroo Point residents, and spans 7 to 8 being the Kangaroo Point approach. The bridge is visually more permeable compared to other truss or arch former structures. The main mast with the cradle legs provides clearest sight lines and accommodates a major rest node in a location that will give great vista to the whole of the city. And it also accommodates other viewing nodes spread across the bridge, so it becomes a bit of a destination piece. It doesn't require large foundations in the Botanic Gardens, which basically a suspension bridge would have required, and has gentle grades where possible, and is DDA compliant with shading for pedestrians across the length of the bridge. It's articulated with 3 expansion joints, one at both abutments and one around Pier 3. And it also integrates commercial opportunities on the bridge, which is something new and unique to this bridge in the city. So how do we come to this general arrangement? The plan you can see here shows the horizontal alignment from Alice to Edward over to Scott Street, which best accommodates the grades and clearances. physical constraints that the project's having to challenge is there's a 10-metre grade difference between the abutments at the Kangaroo Point side and the city side. So we've got to get over that height difference. The navigational channel imposed a constraint on that, so we couldn't have it in the middle. It's been offset to close to the Kangaroo Point side, and that's really largely driven about being able to give enough length to get the proper grades back down to the city landing. So Kangaroo Point Kangaroo Point side is higher, the city landing side is lower. So the height, the navigational clearance that we're left with is the same height equivalent of the Captain Cook Bridge. It was, in early days, it was unfeasible to consider matching the height of the Story Bridge clearances, which are around 30 metres, not 12.7, because that's largely driven because the extent of the approach works would be a visual impairment and take up an enormous amount of effort at both abutments. In terms of land, look, both abutments are located on council roads or over park that's controlled by council, so that's been quite simple. But we've also made sure that there's a wet lease on the Stanford Hotel that we have avoided, so that's added to a bit of the shape. Also, the city abutment is located in the outside the heritage listed botanic gardens, and also I mentioned there avoided the Stanford Plaza wet lease area. And we also undertook flood modelling to support the planning approval of the project, and that was also influential in setting the spans around the main channel flows for the project. As I mentioned previously, here's a long section of what I was talking about there with grades. You can see the navigational channel has been moved to the east as far as possible. This means that the challenge was to maintain suitable grades up to the clear from the city landing to get up to over that navigational clearance, allowing for the structure and rest stops and other viewing platforms. This was largely achieved. We introduced a kink in the alignment to give additional length, and it also avoided having any extensive overland ramping on the approaches, which could be an impost to how that actually all works together. So on the Kangaroo Point side or CT White Park side, we introduced a lift as well that better connects the river's edge to the bridge itself. So you've got a direct access, but when the bridge is, for example, if it was to flood and if that lift was out of service for whatever reason, you've still got the on-road access availability to get down to the river edge, although in that circumstance you wouldn't be doing that. Maximum grades utilised are under AS 1428 with 1 in 20 grade for 19.5 metres and 1.2 metre flat landing. So that gets us up to those over that navigational clearance. Okay, so bridge form. This was always going to be one of the most impactful considerations for the bridge itself. In developing the business case and reference design, selecting the bridge form, there were a number of considerations taken into account. We looked at a range of bridge forms that included a range of single mast cable stays, both with the mast close to the city and to Kangaroo Point. We looked at double mast cable stays, symmetrical, asymmetrical. We also looked at a suspension bridge, as well as forms of various mast inclinations and even possibility of deck curvature. And the form selected and recommended as the reference design was a single cable stay with the mast located close to the city and away from residents. It provided the clearest sight lines through the main pier and less impost in the vista as you looked across the river and from along the river's edge. And it creates a landmark location that's uniquely identifiable with viewing platforms, and also position the piers such that the main channel flow was unimpeded as much as possible. So this is a cross-section of the bridge itself. So starting from the top in terms of shading, we did some early technical studies, looked at this alignment with Brisbane's specific sun environment in mind, and we identified that a lightweight shading on the northern side is most suitable. Continuous shade covering as experienced successfully on the Kangaroo Bridge. In terms of overall width, Council gave consideration to separating people and cyclists. That was our main consideration, definitely in terms of safety and also in recognition of the bridge acting as both a destination place and movement of people across the river. So you've got people wanting to stop, dwell, enjoy, walk, stroll in groups, as well as people in a daily commute needing to get across. So in short, we specified 6.8 metres internal deck width. That's largely made up of 3 metres for walking. That allows for more than 2 people side by side. A 0.3 metre buffer between cyclists and two-way cyclists and pedestrians. And this was largely following a recommendation and benchmarking at the time around Brisbane network, giving that extra 300 millimetre buffer and allowing a 3 metre two-way cycleway plus a half-metre clearance to the balustrade, which is equally found across Brisbane. So below that, you'll see the superstructure made up of steel box girder, concrete decking, upturn and balustrades that allow for, we've also got service ducts in the deck itself. In terms of the city landing, the 2 landings we've got, the city landing reconnects the botanical gardens and the former tram turnaround and engages with the river's edge and supports safe and comfortable movement of pedestrians and riders. It's a signalised intersection there and a raised crossing at the corner of Edward and Alice Street. That enables e-scooters and cyclists to directly access the city link pathway in the city that's been recently installed. And both the City Landing Plaza and Scott Street landings, at the entrances, we have some signature planting positioned and areas are provided to manage the conflicts. So we've also got bifurcation at both approaches to both landings to try and use that as speed reductions. And also the bridge deck bifurcation at Kangaroo Point enables a really good visual connection from pedestrians and people to look down to CTY Park, and also enables a nice gateway into that landing. Back to heavy engineering with the geology. Look, since Council did Clem 7 tunnel in 2005, Council's gathered a lot of geotechnical information in this area between 2005 and 17. You can see from the diagram there, we've largely narrowly fernvale beds in the purple there underneath, a good rock foundation. Above that is alluvium, which covers most of the east, across most of the river to Kangaroo Point side, where we have transitioned to a Brisbane tuff layer and overlying narrowly fernvale. So Council did its own on the reference design, which the piers here in location have followed. So that's been able to be used by the contractor. Did investigation interpretive report. Its foundations are all board pile foundations with steel liners, with the large piles on Pier 4 in the middle which support the main mast, up to 32 metres long in some locations. So relatively straightforward, but still has to be done correctly. So procurement of the project. In 2019, COVID impacts were starting to be felt around Brisbane and the country, and Council announced the program that Kangaroo Point would kickstart the economy and deal with that at the time. A market sounding exercise was undertaken where Council engaged with 15 major contractors, and from that, what we wanted to gauge was the level of interest in the project, identify any potential barriers to success of the project, and to understand the market view on risk allocation, its preferred delivery models, procurement processes, and timeframes that they thought would be achievable. What we found was that the market was saying that planning approval was a major hurdle in terms of risk allocation and time. Collaborative contracting models were preferred, and the D&C lump sum and contract only didn't gather a lot of support during that period. This helped council confirm its procurement strategy through introduction of an EOI process, where we were able to select 2 to 3 contractors to actually go through the tender process. Council undertook the planning approval for the bridge based on the reference design and minor changes with the final tender to really help that time frame and risk allocation. And interactive tendering through early contractor involvement process was adopted to better inform final tenders. So the final contractual model adopted was it's a design and construct contract model, but the payment mechanism is cost reimbursables with a risk reward payment mechanism. In terms of sustainability, Council has recognised the opportunity for Kangaroo Point Bridge to positively contribute to a number of areas: urban design, heritage, environment, stakeholder engagement, climate resilience and energy. So the project is registered for an infrastructure sustainability rating under IS version 1.2, and this will see ratings being applied for both design and as-built and operations. So there's a number of elements we've included there: solar power, most of the power coming from renewables and alike. So finally, commercial activation. This is something unique to the Kangaroo Point Bridge and I think bridges in Brisbane in general. Council, in going to tender, took the opportunity to open it up to the market to include commercial activation into the bridge. The final design of the Kangaroo Point Bridge includes 2 unique riverside dining opportunities. One includes an above-water restaurant and bar on the bridge itself, just before Pier 3, and also on the river's edge with a city cafe opportunity. Those council's currently procuring those operators at the moment. It's out to tender, and the commercial opportunity was really opened during tenders, so we could open it to the market to come back with what they felt was a good opportunity for some unique locations. So the returns from these really will go towards contributing towards ongoing operation maintenance of the bridge, and really adds to a destination piece for Kangaroo Point going forward. So on that, I'll hand it over to Bram.
Thank you, Jim, for your input. I'd now like to welcome our second speaker, Bram Grewers. Bram has more than 25 years of experience in the construction and engineering industry, working with BESIX Group across 4 continents. As a General Manager Operational Support at BESIX Wattpac, he supports the full life cycle of projects and has worked on city shaping projects across the globe, including the Dubai Water Canal, the Dubai Tram, and the Garhoud Bridge. Bram is part of the management team for the Connect Brisbane Consortium, building the Kangaroo Point Green Bridge, and his role includes coordinating the engineering, overseeing operations, and representing the lead contractor, BESIX Wattpac. Please welcome Bram Grewers.
Good afternoon. I would like to start by acknowledging the traditional custodians of the lands we all meet today and pay my respect to their elders past, present and emerging. I also would like to extend that respect to any Aboriginal and Torres Strait Islander people present here today. My name is Bram Grewers, and I'm the General Manager Operational Support for BESIX Wattpac, and also the contractor's representative for BESIX Wattpac on the Kangaroo Point Green Bridge. It's an honor for me to present today some of the engineering complexities that we have worked through during the design and the technical challenges of the delivery of what will be, for sure, becoming an iconic landmark for the city of Brisbane and a real legacy to the community of this wonderful city. Here's the agenda of my presentation for today. I will first walk you through how we moved from the reference design to the concept design. Then I'll give a few details on the wind tunnel testing. I'll talk you through the construction methodology. And then I'll go into a bit of detail about the thermal modeling we did for the big pile concrete course. I'll show you how the Pier 4 formwork, which is the most complex formwork, moved from design to fabrication. And I give a bit of insights into the permanent and temporary works interaction. Then I'll move to the logistics and the material handling complexities. And I briefly touch on the dynamic responses requirements for this bridge. Finally, I talk to the BIM that we've used to integrate permanent and temporary works. So during the ECI phase, we received a reference design and a project brief from Brisbane City Council with the objective to refine that design and come to a concept design that would then be delivered during the delivery phase. The reference design is shown on the picture of the slide. It was defined by the site constraints, the operational constraints of the Brisbane River with respect to maintaining a navigational channel, and of course, through extensive consultation with stakeholders and the community to get a buy-in to the project. Therefore, the focus of our team during the ECI phase was to find efficiencies within the envelope as defined by the project brief. Some of the structural optimizations that we have worked on resulted in an architectural outcome that respected the objectives of Brisbane City Council, and this in close collaboration with the architect of the reference design. The first step was to reduce the number of cables for the cable-stayed bridge by increasing the distance between them at the bridge deck. The design went from 10-meter distance between the cables to a 16.6 meter between the cables, and effectively reducing the number of cables to be installed by about 30%. This also meant some of the cables need to be slightly heavier than in the concept design, but the overall outcome improved the visual appearance and transparency of the structure, which was a major objective for the project. From a constructability point of view, reducing the number of cables also meant reducing the number of anchors, and therefore was definitely a more efficient design. The second tweak to the design was the adaptation of the steel mast structure. The cross bracing at mid-height was introduced. This effectively reduced the free length of the mast legs and acts as a buckling restraint, allowing to slim down the legs significantly. The overall steel quantity for the mast was reduced by approximately 25%. In addition, it simplified the installation of the mast structure by reducing the required number of critical lifts to only 10, and therefore also reducing the number of in-situ welding joints. From an architectural point of view, the slimmed-down structure met the objectives of transparency of the structure. In addition, the legs were rotated over 45 degrees to face the predominant wind directions with the corner of the leg, rather than with the full face of the leg. This had a significant improvement on the wind performance of the mast structure. The third major change was done to the steel block section of the bridge, by reducing the construction height and weight of the structure. The composite box section was designed with constructability in mind by having precast elements to form the bridge deck before a topping slab is cast on top. The reduction in box section height had as a secondary effect an improved wind performance and the possibility to improve the gradings of the bridge while maintaining the required air draft for the navigational channel. Again, the reduction of the bridge height contributes to the architectural objective to have a transparent structure. So you can see now on this slide how the design development led during the ECI phase to subtle changes to the concept design, and we came to the reference design, we came to a concept design as shown on this slide. As the bridge is a very slender structure and is subject to crosswinds due to its location over the Brisbane River, the wind performance of the structure needed to be verified during the detailed design phase. A full-scale model of the bridge in a 1:100 scale was built in a wind tunnel, including the surrounding landscape of both the CBD and Kangaroo Point. As the bridge will be constructed over a number of years, there are intermediate construction stages that may have additional or even greater risk of instability due to wind action. Therefore, a number of critical construction stages was also tested in the wind tunnel. This included a test with the piling fully built, with no cables attached to the top, and a test with the main span partially built, connected with its cable stays to the main piling, but not yet connected to the approach span at the Kangaroo Point. This created a cantilever of approximately 120 meters across the river. The wind tunnel testing didn't show that there are any aerodynamic instabilities for the range of wind speeds considered at the Brisbane River would be occurring. I'll now talk you through the construction sequences, or at least the main construction sequences of the bridge. We started off, as shown in number 1 here, with the pile foundations. The substructure, board piles with both on land and the river. The piles vary from 1 to 1.5 meter to 2.1 meter in diameter for the marine piles. Pile caps are then installed on top of the piles to receive the concrete piers with an architectural shape. In order to install the future composite steel bridge deck, temporary portals are installed across the alignment of the bridge, which will allow us to bring the bridge deck elements in lengths that can be transported and installed by crane barges. These portals will be removed after completion of the bridge deck. Once the substructure is completed, the bridge deck modules are being installed for the approach spans. The concrete diaphragm at the central pier, number 4, is then constructed. Then the pylon at pier 4 is installed, in addition to the modules at span 3 and 4, which complete the bridge deck from the city side to the main pylon. To install these heavy steel sections, a massive tower crane will be installed next to pier 4 on a temporary pile foundation. I will come back to this later in the presentation. Once the main piling is complete, the main span and span 6 can be installed. The main span and back span can be connected to the pylon with its cable stays. The substructure is quite a complex operation and needs to take into account that it's largely built in the Brisbane River. Logistics are a key aspect of the design development, by precasting the pile cap shells in order to minimize formwork installation within the tidal area. This required detailed temporary works engineering for the installation of these shells on the piles, and it also had to allow for the upward pressure of the water on the shells once the shells are made watertight around the piles. The architectural piers will then be cast with bespoke steel forms based on the pile caps. The integration of these steel forms with the reinforcement steel and the concrete sequencing has been a major exercise in its own right. The main pylon will be constructed with a Fafco M2480 tower crane, one of the largest tower cranes in the world, installed on temporary piles next to the main pier. This methodology was chosen to minimize the number of lifts and joints to be done on site and maximize off-site fabrication. The total number of critical lifts is limited to 10 elements. This is 4 bottom legs, a cruciform element at mid-height of the pylon, 4 top leg elements, and a top pyramidion. The top pyramidion houses the cable anchors and weighs approximately 150 tons. This will be installed with a single lift. The superstructure is composite steel box section with a concrete deck. The box section has two wings either side of the bridge, which have a dual function. One is to improve the wind performance of the bridge deck, and secondly, they serve as formwork for the in-situ part of the bridge deck. The bridge sections will be transported from the port of Brisbane to the city along the river, and then installed by crane barges on the temporary portal before being connected to the already installed sections and the concrete diaphragm at Pier 4. The largest sections are those of the main span, which will be installed in 3 sections of 60-meter length each and are weighing each approximately 170 tons. The effects of the temporary stages of these elements during transport, lifting, temporary construction stages are all being considered into the design, as some of them are critical to the overall structural design of the bridge deck. In order to guarantee the long-term durability of the concrete, strict temperature control during the casting and curing of the concrete needs to be maintained. At one end, the maximum concrete temperature needs to remain under 75 degrees centigrade to avoid the late intringite formation. In addition, the differential temperature needs to be restricted to avoid early cracking in the concrete while it is curing and building up its strength. The large diameter piles in the Brisbane River pose the biggest challenge as they are in direct contact with the water of the river, and therefore the external surface of the piles is continually cooled down by the water in the river. In close collaboration with the concrete supplier to create a low hydration mix, we undertook extensive temperature modeling and stress-strain analysis to model strength and stresses created by the temperature evolution over the curing period. The models were benchmarked with test samples which were placed in the river with thermocouples prior to casting the main piles. This led to an excellent correlation between the model and the actual temperature measured again with thermocouples when casting the piles, and therefore the confidence that predictions of the model are accurately representing the actual behavior of the concrete during the curing period. Pier 4 is the main pier underneath the main mast, and it has a very complex shape with 4 arms starting from a stem which is on top of the Pier 4 pile cap. In view of the large bending moments and shear force exercised on this pier, the concrete is also heavily reinforced. The temporary works engineering for the formwork has been extensive exercise with a close coordination between the permanent works design, the reinforcement scheduling, the temporary works design, and the casting sequence of this pier. We started off with the concept design of the formwork, which is supported off the pile cap. As the footprint of the pile cap is smaller than the projection of the arms of the pier on its top plane, the support structure is required to withstand the forces of the wet concrete and casting into the forms. This mega frame, as we call it, sits as a working platform on top of the pier in order to receive the formwork for the pier. This required close collaboration between the temporary works and permanent works designs. In the detail design, special attention was given to safe access for the reinforcements installation and for the concrete casting crews. The formwork fabricator was then able to create his shop drawings from the design model and fabricate the formwork. The mega frame and formwork was fabricated off-site in elements that can be disassembled for containerized transport. We then assembled the elements in our logistics yard at the Port of Brisbane before bringing them to the site with barges over the river. As explained before, a number of temporary portals have been designed to receive the steel deck elements, which are being transported to site and lifted into place by crane barges. These portals are all designed with access to welded deck elements in mind. The porters will be removed after completion of the bridge deck. Another aspect of temporary engineering are the barge, crane and rigging studies for all the steel elements that will be installed. These include lifting studies, crane positioning, effects of lifting forces on the permanent structure, logistics to bring the elements to site, design of temporary supports, and stability checks by naval architects. Again, a close collaboration between the temporary works and permanent works designers is essential to come to a successful outcome. With the bridge being built in the middle of the city and connecting to Kangaroo Point, which is densely populated, logistics of bringing large elements to the worksite needs due consideration. First of all, there are physical restrictions imposed by the width of the access roads, and the turns which need to be taken to reach the site at the city site or at Kangaroo Point site. Secondly, there are restrictions due to the traffic in these areas, imposing out-of-hour works to bring large loads, creating other challenges with respect to noise control. Therefore, a strategy to bring as much as possible over the water and use the Brisbane River as the key supply route has been chosen. This requires a logistics hub at the Port of Brisbane, where all major components are loaded on barges to transport them along the river to the workfront. Logistics Hub has its own loading jetty with crane to service the project. The main elements that are brought in over the river are the piling materials, the steel reinforcement, the steel deck elements, precast concrete elements, and temporary work items, for example, steel forms for the piers and all the temporary portals. Using the river as the key supply route has contributed to an excellent relationship with the community at either side of the river during the construction phase. But it required specific thinking on how the bridge elements would be designed and constructed. The final design point I want to touch on is the dynamic response requirements for footfall. As you all probably are aware, the Millennium Bridge in London demonstrated the need for correct assessment of the footfall analysis. A detailed numerical study has been done to assess the risk based on the natural frequencies of the bridge. The study has demonstrated that there is no risk to the vertical and horizontal comfort criteria. However, to mitigate the risk of lateral locking, a 5-ton tuned mass damper will be installed at mid-span of the main span, which will allow to adjust the response of the structure to footfall and can be tuned after in-situ testing if required. As you may appreciate, throughout my presentation, the detailed design and delivery of a bridge of this complexity is only possible through close collaboration of a significant number of specialist engineers. A total of 20 different digital models needed to be coordinated during the design. To facilitate this collaboration, B6 Wattpack set up a collaborative BIM model in Revizzo, which included all the design models, the temporary works models, the equipment, for example, tower cranes, crane barges and hoists, the reinforcement models, the shop detailing of the precast elements, the services models, and so on. These models get federated on a weekly basis with coordination workshops to work through the interfaces, clashes, before construction happens. For the engineers working on the project, it has been a great experience to use these collaboration tools and work in the digital world. The models are also an excellent asset to explain to a wider audience construction sequences and impact on local existing facilities and infrastructure. This is the end of my presentation.
Thank you, Jim and Bram. It's now your turn to get involved. Please ask our speakers questions via the chat box, and who your question is directed to. Thank you to everyone who submitted a question while you were registering. So looking at the questions, first question I've got here, Bram, is for you. So what are two main challenges encountered in the design of the bridge and how was it overcome? And that's from Edgar in Queensland.
Thanks, Eliza, and thanks for the question. Look, the bridge, of course, is quite a complex technical structure, and there's a whole number of challenges. But if you look at the main technical challenge, I would say really the wind performance is something which needs real good consideration. The bridges across the Brisbane River, where you have crosswinds against the bridge, against the pylon, and against the bridge deck. And then there's the different construction stages that also need to consider, like I explained in my presentation. So we've engaged a specialist wind consultant to do a desktop analysis first, and then we validated that during the detailed design with a wind tunnel test to make sure that the wind performance is acceptable. I think a second element and a second challenge for this bridge is the interface between the temporary and the permanent works design, and definitely with the different construction stages, because it's not a bridge that is wished in place. It has a number of stages to get there, and we had to do a whole lot of constructability workshops with the designers and through the full design cycle. And to model also those temporary and permanent works. And we did that also in a federated BIM model, which again helped us to identify the interfaces and those challenges.
Great, thank you. Bram, I'm curious about the first part of your response about the wind tunnel testing. Did you need to make any adjustments to the design as a result of the wind tunnel testing?
Good question, Eliza, and it was identified as one of the risks when we went to DCI, because we didn't have the time to do the wind tunnel test during the ECI period, so we could only do it during the detailed design phase. But we had a good desktop analysis and a good assessment done during the ECI, and then the wind tunnel didn't require us to do any adjustments to the profile of the bridge, which was a very positive outcome.
Great. Jim, I have a question for you from Neil in Queensland. What was the greatest hurdle during the planning phase?
Ooh, okay. So I would say, in planning sense, once you've selected your alignment, getting the horizontal alignment nailed down, which was a combination, as I explained. We're solving a problem of getting over the river with a 10-metre height difference, and you've got to fit a navigational channel in there. So that's one constraint that sort of is interactive within itself to solve. That's really what drove the reference design in that civil perspective. The second challenge then would be this reach of the river. We're introducing a bridge or potential visual blockage, etc. The Kangaroo points are very sensitive to people in Brisbane, etc., keeping that vista alive. It was about selecting the form of the structure and how that would impact on whether it's contained within the river or was it reaching out into the approaches, and in particular the botanical gardens.
Okay, thanks, Jim.
That answered that. That gave me nightmares.
So Jim, I have a question for you. A bridge is part of a link. Provides a missing link in a network. So what have council done to ensure that the bridge connects into the network efficiently and safely?
Oh, good question. Look, to expand on that, don't forget, this program's the first of creating a series of active links across the Brisbane River. It's a very windy river. We've got very few locations at the moment that someone can easily access to ride or walk. This is the first one. Obviously, yes, it does need to connect with ongoing network connections to get that benefit. So we've recently done CityLink in the city. We did some advanced work and moved it from the Stamford side to a line in its final arrangement at the moment. So it ties directly in with both the being able to go back into the gardens onto the Riverwalk side, but also into the CityLink in the city. On the Kangaroo Point side, also where they're now tying into the Eastern Corridor active transport, or I should say riders, walkers in that direction, basically hooking up with Deacon Street through currently at the moment, thinking through, and the Wollongabba area as well. So in the stadium for when 2032 is. So that'll be a big connector, during the Olympics when that happens.
Yeah, absolutely. Bram, I have a question for you. It's related to construction. How do you plan for the risk, safety of workers and the public, properties and traffic, considering the complexity of the project?
Look, this is of course one of the main considerations and look, part of responsibility as a contractor to deliver the bridge safely. It all starts off with safety and design and making sure that during the design development there is ongoing engagement with the designers to build in the construction methodology into the design. That's the first step. But then after that, our engineers they work really extensively on what we call construction method statements, and they go to the detail of how everything is being built. It includes things like lifting studies, swept path analysis for bringing in the different elements of the bridge. It looks into installation of hoardings, access for the public, and it looks into also how the workers can safely access the different parts where they need to work. For example, the temporary portals that we have in the river that we will use to, to, to put the bridge deck elements on, and where those elements need to be welded in place. But those portals are already engineered and designed with access for the welders. So it's all those elements together, which is a big part of the job that's being done during the delivery. And there's a good team of engineers working on that on the job on a permanent basis.
Thank you. There's a few questions with a similar theme, so this might be a two-part answer, but the first part of the question is how does the design address climate change, such as flood? We all know the Brisbane River floods, so flood load and vessel impact load. And the second part is earthquake loads. So Jim, do you want to go first?
I might jump in the first one. Question relating to climate change and flood. I suppose, look, as part of the planning approval, we undertook some extensive flood modelling using the Brisbane River Catchment Flood Study model that was created after the 2011 floods. And within that's got sensitivities around climate change in that respect. What was the second question there? Second part?
About vessel impact.
Vessel impact. So, look, we engage with the harbour master through leading technical studies leading into the reference design, and I think that question is more in relation to we're able to select the appropriate vessel type for impact loads on the pier itself. So, you've got to be pretty careful to designing it to AS5100. That'll design for the fluid flow loads around your piles, your bulk caps, under flood arrangements. but you also need a vessel. And the interesting part of that is that the vessels have really changed over the last 50 years with the change in the use of the river itself. No longer do you have big barges coming down with sediments. With pea gravel and all that sort of stuff. We're now into smaller, more people transport orientated, and maybe the odd 200 ton barge that's being towed around, like we've got out there at the moment.
And maybe I can tap into the earthquake loadings. Of course, the bridge is being designed for earthquake loading. This is part of the structural design that's being done. And it's in accordance with the AS 5100. And I think, if not mistaken, but I have to look this up, there is is it bridge design or earthquake design category 3 that it's designed for? Yeah.
Thank you. Next question is for Bram. I've got a question from Nathan in Queensland. AS 5100 sets out some very onerous deflection requirements for pedestrian bridges, which in the past we've found difficult and commercially unviable to comply with for cable-stayed structures. Was there a project-specific approach to this requirement, or how is this addressed economically during design?
Yep. So yes, there has been a project-specific approach taken because, as you rightfully mentioned, the requirements are quite onerous, and we've also realized, and we've already discussed during the ECI phase with the council and also with Arab, that it would be better to have a reduced live load under SLS to check the deflection requirements and to avoid encroachment of the navigation channel. And that was then defined as the requirement of having a 3 kPa reduced live load for this specific load case. There were a few other conditions to that. I think under the permanent load, we should demonstrate that there was no places where water could stand on the bridge deck, and a few additional conditions with that. But there was definitely a project-specific approach taken here.
Yeah. Jim, a question for you from Ben in New South Wales. Do you expect the bicycles, e-bikes and scooters to become increasingly popular in the Brisbane CBD? And I suppose how does that allowed for in the design of Kangaroo Point?
I'll look quite simply. The first answer is definitely they are popular. Certainly, I think since 2018, there's been over 8 million trips recorded from a shared user point of view, and that's before we even talk about the privately owned ones that are now entering the network at the moment. And what was the second question there? Sorry to keep asking you that.
No, that's all right. How is that allowed for in the design of the Green Bridge, of Kangaroo Point Green Bridge?
Oh, look, they can all. They've got capacity to use it within the shared bikeway with cyclists. That's where they go.
Thanks, Jim. Bram, a question for you. It's from Max in Queensland. What fatigue modelling has been done, and when does fatigue become an issue for large span cable-stayed bridges? Presumably wind load fatigues in this case rather than bridge live loads.
Yeah. So fatigue is typically a consequence of vibrations, and the approach taken is really here to avoid fatigue by limiting the likelihood of ongoing vibrations in the bridge. Again, this was achieved by doing proper wind modeling and designing the bridge elements, having a good response to the wind effects by selecting the right profile of the different sections. Of course, in cable-stayed bridges, you can also have fatigue stress in the cables, and that was overcome by dampers at the bridge deck where the cables are connected to the anchors.
Jim, a question for you from Mihindu in Victoria. How important do you think it is to carry out flood data analysis as part of the preliminary investigation for bridge design?
That's a very good question and a very good basic question before you, as you create the solution to crossing the river or anything like that. Brisbane is in a floodplain, so we've got to be very cognizant of how the river behaves and working around that. That's why we use the flood model that was developed after the 2011 flood. In how we use that is to be able to set and minimise the impact that we could within using those flood models to set your pier locations. That sets the spans, the structures that you've got to do. That's all integral in that initial planning phase of what is the solution and the constraints you need to address. We've got it across the river. That's why you don't have a solution that's got piers at 20 metre centres. That could be a very efficient structural solution, but it would have massive flood impacts on the performance of the river. So, yeah, that's very sensitive to the Brisbane environment.
Jim, another question for you. So, why was the bridge chosen to be built in its location, in its chosen location?
I suppose you go back to the 2014 initial study when council got serious about building a bridge there. I think I mentioned that I think it was originally conceived around the 1860s that a crossing here or Victoria Bridge. Eventually, it was selected to go Victoria Bridge, and I think the first one didn't last too long. I'm drifting with that answer, but bringing it back to the reach we're talking about, you've got the Story Bridge, you've got Captain Cook Bridge. We did a study that broke that up into 4 different areas, and we really needed to identify if you're putting a crossing here, what are the constraints, what are the benefits that come with that, and it really through that option study, it nailed down to those 2 options. It was obviously really the corner of Alice and Edward Street, but where did it connect to on the other side? Initially, it was Thornton Street as a possibility, but really Scott was the other alternative, and Scott was the one selected through the business case and reference design.
Thank you. Sorry, Jim, I've got another question for you. How does Brisbane City Council see the long-term strategy for green bridges for Brisbane in conjunction with the 2032 Olympics? And that's from James in New South Wales.
I suppose there's two aspects to that question I could see wanting to be known. One, look, the program, we're underway with 2 bridges. We've had a flood. Council's dealing with how that's impacting the city as a whole, and impacts, no doubt, obviously on budget and expenditure. So the West End bridges are on pause, but we've also we've issued a notice of intention to resume on 600 Coronation Drive to lock in the land for any future bridge that goes there, given the development underway there. So look, future planning, future proofing in that aspect, but in terms of when and that comes on board, that's not something I could answer now. It's just on pause. That was that. What was the other thing that going through my mind there was... so you can go back to the question again. I have to ask you this all the time, don't I?
How does the Brisbane City Council see the long-term strategy for green bridges in conjunction with the 2032 Olympics?
And look, I think we've got to be also cognizant that this bridge was already underway before the Olympics was announced. So we were heading down this direction to build this bridge in this location. It also complements the activities around 2032 when you'll be getting people to move around the city. So it'll be absolutely paramount for people from the CBD, for example, to then move to the Gabba. It's a real key piece for people to move in that direction. So it's complementary.
Right. Thanks, Jim. Bram, a question for you from Lewis in Queensland. What was the main engineering challenges in constructing the bridge?
Look, the bridge is still under construction, so there's still some challenges ahead of us. But I think a few of the main challenges that we have is, of course, due to the location of the bridge in the city center and the access restrictions of bringing large pieces of equipment and large pieces of structure through the streets at either side, Kangaroo Point and City side. It's the whole logistics of building a bridge or a structure of that size in the city center. So we've chosen to use the Brisbane River as the main supply route, having a logistics yard in the port of Brisbane, and then using barges to bring the large elements to the river, no, to the bridge location. I think the other challenge is the, the the interface between temporary works and permanent works, and also especially the shape and the complexity of the piers with the interface of the reinforcement of the different elements. As you can imagine, you have starter bars sticking out of the piles who are interfering with the reinforcement of the pile caps, and then you have the reinforcement of the pile caps that's interfering with the starter bars going into the piers. So all that modeling and that detailing is definitely a bit of a challenge, and the engineers again have modeled that in detail, trying to make sure you have as least as possible surprises on the job site when they're constructing it. So I think those are two main challenges that I've seen from the construction point of view.
Thanks. Jim, question for you. Why is the bridge a green bridge?
Green Bridge. Look, in essence, it's about changing the mode of transportation across the river. You're getting people to walk, ride, whether it's a cycle or e-scooter, and basically getting them onto that mode of transport would takes them out of motorised vehicles on the road. That would be the best way for me to probably summarise that. That's what that's really the essence of it: getting people moving, active, as opposed to using petrol in a vehicle.
Bram, question for you. And I know you talked about it a little bit in your presentation about the dynamic performance of the bridge for pedestrian comfort. Do you elaborate a bit
Yes.
further on that?
So yeah, the dynamic performance, of course, is quite important, and specifically for pedestrian comfort. So it's something that's very detailed desktop analysis has been done, and with the mass tune damper that we have in the center of the bridge, we can tune that based on dynamic testing that we can do once the bridge is complete, to make sure we remain within the comfort criteria that are specified. Um, Currently, we don't foresee any issues based on the numerical modeling, but it's always good to have that contingency plan in place. And if we would see that there is an issue when we do the testing, the damper can help us to get to the right performance and the way that the bridge behaves under pedestrian loads. Um, the I would say that yes, for sure, with slender bridges, this is always a consideration. But I think also the industry and has learned a lot over the last 20 years on how to deal with this, and really have really key experts on board to manage that. I think we should have a proper outcome once the bridge is complete.
Thank you. Another question for you, Bram. How deep is the bedrock on both the city side and the Kangaroo Point side?
You're testing my memory, Eliza. I think the deepest piles are about 30-meter deep. So these piles are board cast in situ piles. Essentially, it's steel sleeves that are being driven with first a vibro hammer and then an impact hammer into the bedrock. So we get a seal of about half a meter into the bedrock. And then we drill, depending on the loading on the piles, another couple of meters into the bedrock to get the, the full strength of the bedrock, plus potentially, if it's required, also tensile strength there. So in the middle, it's about 25 to 30 meters, and of course, the bedrock goes up to either side towards the city and the Kangaroo Point side. I won't cite the exact depth there because I don't know by heart, but it must be in the around 15 meters to 20 meters max.
Okay. Probably a question that I can throw out to both of you. How is the bridge future-proofed?
Look, there's a number of things, of course. First of all, the design criteria have taken into account flood levels over and above what's expected. I think some of the flood levels are have a 1 in 2,000 years return period that we have to consider. So
Yep.
that's one way of future-proofing the bridge. I think another part and a big part of it is making sure that we get the maintenance provisions for the bridge embedded in the design. And so we've engaged actively during the design development with the maintenance team of council to make sure that from an ongoing maintenance point of view, access is foreseen and it's clearly known of what needs to be done. So I think it's also an element of future proofing. And I think lastly, there is of course being being a green bridge, we want it to be a sustainable bridge. So we've embedded, for example, solar panels on the canopy in order to produce electricity for the bridge through solar energy. And Jim, there's maybe some other things you want to add to this?
Yeah. There's the two that come to mind very quickly are one, in setting the width of the bridge at 6.8 meters. That's wide. That's more than generous for now and probably numbers in the future. It's really that width, I think, has been there to also enhance the destination aspect to the bridge and being able to really make it usable and separate between riders. So there was future proofing in that. And the other one was, look, we just want to be cognizant if a stay needs to be replaced, that was integrated into the design and O&M considerations. There had to be designed that if one, not to say a stay failed, but if something happened and you wanted to replace it, it wasn't detrimental and having to come back and do crazy things. So they're probably the two things that come to mind straight away.
Got another question. Might be that another one for either of you. Are there any special materials being used in the design, for example, fibre composites?
Not really, to be honest. I mean, it's all very conventional materials used in a efficient way, I would say. I think one thing,
Yep.
which is quite important for council and sort of speak on your behalf here, Jim, but I think that journey is that we wanted to maximize local content, and so we really looked at using as much as possible local fabricated materials. So, for example, all the steel is being manufactured in Australia, is used from Australian mills. So it's not special material, but there are certain conditions that we have to adhere to in choosing the materials for the bridge.
Yeah, I wouldn't have
I have
anything.
a question for Jim. Was there any possibility to extend the cycling and pedestrian capacity of the Story Bridge rather than adding in an additional bridge?
I understand the concept of the question, but really the real network advantage is the crossing and location where it is. The Story Bridge itself, it was planned ahead of its time and was built 1940. It's done well to service at this point. Adding something, it's already got a facility to cross there, and it's not at capacity, so you wouldn't need to expand it. The real advantage of the network location of this bridge is it connects. It connects directly into the city. It plugs the gap between the go-between bridge and the Story Bridge, so it provides that other opportunity to distribute people more efficiently, safer, and get them active again.
Thanks, Jim. Got another question. Could be for Jim or could be for Bram, but it says, question for Jim: were any particular treatments for cyclist lane separation required near the restaurant location?
The best part to that was putting the restaurant above. We actually don't have any impairment. That all the sight lines are covered, and I think we also made the approach there wider, far wider than it needed to be. So it's accommodated that. So in summary, one, we've placed commercial opportunity away and over, so cyclists and pedestrians are unimpeded in their transport. But we've also, because it's a curve around that point, we've also made it wider. So all the sight lines and everything are intact.
Right. I think we're probably at the end of our questions. Thank you, everyone. That's all we have time for today. Thank you very much to Jim Heffron and to Bram Gruers for their time and input. I'd like to thank Engineers Australia, industry partner Brisbane City Council, for their support. Please complete a short feedback form which is linked in the description box below to help us improve and plan future sessions. Thank you again for joining us, and we hope to see you soon at our next Thought Leaders event.